and the presence of contact-mediated dormancy.
Yes, thank you very much for the introduction. So welcome everybody. So I will talk about microviral virus epidemics in the presence of contact-mediated host dormancy, and this is joint work with Jochen, as he has already anticipated. So now the question is if this starts working or not. Yeah, okay, now I have to agree that I got recorded, I guess. Yes, okay. So nice. So what are we considering? I mean, this is again, as in Jochen's talk yesterday, a toy model for some biological phenomena. So don't take it too seriously in terms of details, but you want to identify some kind of effects. And here we consider virus infection against a population of microorganisms, for example, bacteria or archaea. And then it has been observed by several authors that microorganisms may enter a dormant state, an inactive state, as part of their immune response against virus attacks. And one important paper is this by Bautista, Zhang, and Whitaker. So they observed this so-called contact-mediated dormancy, which means that basically by the mere contact of the virus with the cell membrane, the microorganism just switches off, and then it can't be infected and it can't spread the virus. And also an interesting thing is what was observed by Jackson and Fineran and Meeske, Makandakari, Higa, and Marafini, that there's this CRISPR-Cas game, right? So there's this CRISPR defense mechanism also for microorganisms, that they somehow identify the DNA or RNA of the virus. And then next time the virus comes, they can just identify it and kill it. But the virus can somehow trick this. And then the next step is, if they can't identify the virus, then the host cells just switch off. And then they also can't be infected. So this is a quite general defense mechanism. And yes, here we will propose a stochastic individual-based model for a lytic virus infection for one cell haploid hosts, including this effect of contact-mediated host dormancy. So let's see what the model is. So we have basically 4 types. And with these 4 types, we have a continuous time Markov chain. And type 1A is the active and susceptible host. Type 1B will be the dormant host, type 1I the infected host, and type 2 is the free virus, the virion. So if there are no viruses in the system, then we have a simple mechanism similar to Jochen's talk yesterday. So it's basically just reproduction and then natural death and competition. So we have the reproduction at rate lambda 1, each type 1A individual. Okay. Yes, so type 1A, sorry. So if there are no viruses, then they reproduce via binary fission at rate lambda 1 per individual. And then we have this death by age at rate mu1 per individual. And then competition is quite similar to Jochen's talk yesterday. So we have this parameter K, which is the carrying capacity, and this is going to be our scaling parameter. So the population size is of the order K, when K is large. And there's this parameter C for the strength of competition. And then at rate divided by C over K, each pair of active individuals which meet, one of them dies, right? And this is death by competition. And here we don't have this competition-induced dormancy, but we will have dormancy coming from the contact-mediated behavior of the system. So I don't know if anyone is still coming. No? Okay. So, right. And this gives this Lotka-Volterra type regulation in the limit k tending to infinity. So we will see the dynamical system for in a few minutes. And then what happens if there are viruses in the system? They will try to attack the active individuals. And there's for some parameter d greater than 0 at rate d divided by k, where k is again the carrying capacity, we have virus attacks at rate d divided by k. And this is d divided by k for each pair of one virus and one active individual. And then with probability 1 minus q, where q is some number between 0 and 1, it's a successful virus attack, which means that the active individual now gets infected and the virus, so to speak, dies. But dying means that it becomes now part of the infected cell. And at some point, there will be potential for lytic virus reproduction. And then the unsuccessful virus attack means that this happens with probability q, that the active individual now becomes dormant due to this contact-mediated dormancy, and the virus just stays a virus. exactly free virus particle. Okay, and then what is the fate of these infected individuals? Either they recover, which happens at some rate r greater than 0, or they die via lysis at rate v greater than 0. And we have a fixed burst size m, which is some positive integer. And at each death by lysis event, basically, it ejects m new virus particles, and it gets exhausted and then dies. So this is how lysis works in our model. And then dormant individuals can do two things. Either they resuscitate, this happens at rate sigma, or they die at rate kappa times mu1, where you remember mu1 was the death rate for the active individuals, and kappa is this scaling parameter. So you compare somehow the rate of death in active and dormant, and this factor kappa tells you what is the ratio between them. And kappa could also be 0 from modeling. From modeling perspective, it's reasonable to assume that dormant individuals sooner or later actually die. But if it's 0, mathematically, it doesn't make a big difference actually. But sigma is always assumed positive. That's important. And then now we extend death by competition as follows. So type 1A individuals also feel some competitive pressure from dormant and infected individuals. And also for pairs consisting of one active and one dormant or infected individual, we have these competitive events at rate C divided by K, where the active individual dies. So I mean, infected individuals can't reproduce, but they still take away some space and some resources from the active ones because they need some energy to produce viruses. And therefore, this also yields some competitive pressure for the active individuals. And we are following here the modeling of one paper by Gubudak and White, which I will mention. And there they also assume that the same holds for the dormant individuals. So I mean, it's a matter of modeling and a matter of the kind of interaction, whether the dormant individuals actually mean some competitive pressure for the active ones, but here we assume that they do. So also if you have an active and a dormant one, then the active one dies sometimes due to competitive events. And then viruses have death rate mu2. This is natural death of viruses, so they just fall apart and they can't reproduce on their own. So they can only reproduce via lysis. Okay, is the model clear? Any questions about this? If it's fine, then let's look at the system again for a minute without the viruses. So if there are only type 1A individuals in the system, then we know from APR and Kurtz that if you scale the population by K, and then look at compact time intervals, then you converge to a solution of this one-dimensional differential equation. So this is derivative of M1A of T is M1A of T times birth rate minus death rate minus this competition C times N1A. And then this is, of course, an easy to analyze system, right? So this has an equilibrium if one of the two factors is 0. So one equilibrium is 0. And the other one is this M1A bar equal to lambda 1 minus mu1 divided by C. And this always exists if lambda 1 is greater than mu1. And it's also asymptotically stable. So any positive solution with a positive initial condition will converge to this equilibrium. And this we call the equilibrium size of type 1A. And then maybe a short comparison with competition-induced dormancies, what Johan talked about yesterday. So there we have this difference that competition-induced dormancy is also triggered by self-competition of the type that exhibits this dormancy. So sometimes two active individuals in that model meet, and then instead of dying by competition, one of them becomes dormant. We don't have this here, right? So here we only see the dormant individuals if viruses occur, and then they cause these unsuccessful virus attacks. And this means that somehow the dormant form of the active individuals, that's just a byproduct of this epidemic, this infection. And therefore the equilibrium population size of dormant individuals in absence of the viruses is 0. You don't have dormant individuals otherwise. Okay, so now I will talk about the first phase of an epidemic, and the branching process approximation. So basically what we want to look at is the following situation. You have a big population of active individuals living in equilibrium, and then one single virus occurs, and then we want to see what happens, whether you have a big macroscopic epidemic or not. So usually we look at this process M1A, TK, and so on with these indexes K. This means that you divide each coordinate by K, because this is the scaling where you can see the dynamical system. So, and the usual initial condition is we have more or less N1A bar active individuals after scaling by K, and just one single virus. So this is our initial condition. Actives are in equilibrium, no infected individual, no dormant individual, and just one virus. And then the question is, will the virus infection actually become macroscopic? So will we ever see a number of viruses comparable to the number of hosts with asymptotically positive probability as K tends to infinity? And I mean, here, of course, stochasticity is important, right? So it could happen that the first virus dies just by randomness, and then we don't see a big epidemic, but it could happen that it manages to infect somebody, and this infected host then manages to produce new viruses, and then in the end, you have a big epidemic. And so if yes, if you see such a macroscopic epidemic with asymptotically positive probability, what is the limit of this probability, and how long will it take until you see a large number of viruses? And then the question is also what happens after a successful virus invasion. So do we have stable coexistence between viruses and hosts, or do we have some kind of periodic behavior? Can it maybe even happen that both hosts and viruses just die out? So like, what is the fate of the epidemic? And then, of course, how does dormancy help the hosts evade infection? So what is the advantage of the hosts by doing this contact-mediated dormancy? Okay, and then we look at this first phase of the epidemic. There, as I said, stochasticity plays an important role. So here we want to somehow employ the ansatz of adaptive dynamics, which has basically two main steps for this first phase. And this comes from the paper by Nicolas Champagnat, but also there are many other papers written afterwards that use these techniques. So the first step is that one should show that the resident population, which is in this case type 1A, this stays close to its equilibrium after dividing by K, as long as the total population size of all the other types, dormant, infected, and virus, reaches epsilon times K for some small positive epsilon, or dies out. So we will not see a big change in the resident population as long as either we have epsilon times K of these invaders, or they already died out. And if we can guarantee this, which is usually done via some standard Friedlein-Wenzel type large deviation arguments, then one should be able to approximate this 3-type population without scaling by K here via a 3-type linear branching process, right? So this means that basically the population of the actives is constant, and therefore all the rates depend linearly on the population size of these 3 types, and then you get a branching process. And then the probability of reaching size epsilon times K and the time until a successful invasion, these should all be expressed in terms of a branching process. As I mean, then you have to take first the limit K to infinity and then epsilon to 0. And in this coupled limit, you have somehow convergence to the survival probability of the branching process and the time until the branching process takes until it reaches size epsilon times K. And then if you have reached this epsilon times K, then we are in this situation, as Johan also explained yesterday, all the 4 types are of the same size, the same order. And therefore now we can approximate the whole system via a 4-dimensional dynamical system, about which I will talk in a few minutes. And then the goal is that if you reach size epsilon times K, then this should somehow also mean that afterwards we have an almost deterministic behavior, and the epidemic persists somehow. So if it didn't die out in the beginning, if it already reaches size epsilon times K, then we want to say that in this case, actually it stays there for a long time. So we have a persistent epidemic. And the question is if this really works in our settings. So how does one do it? Naively, at least. The first step is we assume that the active population size divided by K is just constant equal to M1A bar. So it's just in the equilibrium size. And then this means that if we have some resuscitation of dormant individuals or recovery of infected individuals, then we don't create new active individuals because they are assumed to be constant, but we just discard these individuals, so we just assume that they die. And also, we somehow pretend that instead of virus attacks, we just have some linear rate for events happening for the viruses. So instead of saying that viruses infect here active individuals, for each virus at rate proportional to M1A bar, we have either a successful or non-successful virus attack. So this is really something depending linearly on the number of viruses now, and then we get this branching process. The question is this branching process that we obtain this way suitable for our purposes, or is there any problem with the usual approach? And apparently there is, because if you look at the mean matrix of this branching process, so first of all, I should say, what is the mean matrix? So basically, we have 3 coordinates here, dormant infected virus, dormant infected virus. And in each entry of the matrix, you have the average number of individuals of type J produced by individuals of type I. So here, number of dormant individuals produced by dormant individuals. This is a negative number because dormant individuals can only die or resuscitate. So this is minus kappa mu1 for the death and minus sigma for the resuscitation. For example, here, this minus R minus V, this is the intrinsic growth rate of type 1I. So the infected individuals also don't produce directly infected individuals, but they just recover or die by lysis. But this M times V here, for example, number of viruses produced by 1 infected individual on average. So this is when an infected individual actually dies by lysis and then produces M viruses, which happens at rate V. And then this Q times D M1A bar, this is the rate of dormant individuals produced by viruses in unsuccessful virus attacks. This 1 minus QD M1A bar, number of infected individuals produced by viruses. And here, this loss of viruses in successful virus attacks and loss of viruses due to death. Right, so this is the mean matrix, and we know from standard branching process theory that the branching process is supercritical, so it has a positive chance to survive if and only if this matrix has a positive eigenvalue. And what we can see here is that this matrix is not irreducible. So actually, if you look at the first row here, then we see that minus kappa mu1 minus sigma, which is always less than 0 by assumption, this is an eigenvalue of this matrix, and it has left eigenvector 1, 0, 0. So the matrix is not irreducible. And actually, we can explain this from the model. So what happens here? If you only start with dormant individuals, no infected individuals, and no viruses, then this means that they will all die. Right? So you cannot produce from dormant individuals directly any infected individuals and any viruses just via producing active individuals, but you can't produce active individuals because we are in the branching process where the active population is assumed constant. So the dormant coordinate will always die out when being on its own. And the dormant coordinate is always subcritical. And then this is a problem because we wanted to say that if the population of dormant, infected, and virus reaches size epsilon times k, what happens if all the epsilon times k guys are dormant? Then they will still die out and we will still converge to the equilibrium of the active coordinate without other coordinates. And we want to somehow say that this doesn't happen, right? So if you have epsilon times k of these 3 types, then actually you have enough viruses and enough infected individuals as well, so that you can have a macroscopic epidemic with high probability afterwards. Okay, so what can one do? We basically just change the roles a bit, saying that now not only type 1A is resident, but also the dormant individuals we consider as resident. They reside with active population size 0. And then the invaders are just type 1I and 2. So this means that now we want to guarantee that types 1A and type 1D, active and dormant, they stay close to the equilibrium until the other 2 types, infected and virus, reach size epsilon times k or die out. So this means that now the equilibrium size of dormant individuals is 0. And then we can have a 2-dimensional branching process, just infected and virus. And this is now nice because what you obtain this way is again a branching process that is the 2-dimensional projection of the previous branching process, just the infected and the dormant coordinates. And it has this mean matrix, which is just, if you look at the previous mean matrix, it's the last 2x2 block here. So this means that the 2-dimensional branching process is supercritical if and only if the 3-dimensional one is supercritical. So the largest eigenvalue of, if the largest eigenvalue, or if and only if the largest eigenvalue of this matrix is positive, then the largest eigenvalue of J is also positive, the bigger matrix. And then in that case, if this has a positive eigenvalue, then also the largest eigenvalue of the bigger matrix is positive. And this means that the 3-dimensional branching process is supercritical if and only the 2-dimensional one is supercritical. And this gives this constraint, which is just saying that the determinant of this matrix is negative. So let's try to understand these conditions. So under what condition is this branching process supercritical? So what happens here? So MV minus R plus V times 1 minus QD M1A bar is larger than mu2 R plus V. So what is this? So first of all, we see that if MV is less than or equal to R plus V, then we have a problem because this becomes here negative or at least non-positive, while this side is always strictly positive. So this means that MV less than or equal to R plus V, this means that you don't produce enough viruses in the lytic cycle of the virus. So each lytic cycle is somehow very inefficient, and therefore, whatever the other parameters are, there's no chance for a big epidemic. If MV is larger than R plus V, then this is here positive, and then somehow if N1A bar is large, if you have a large population size for the active individuals, then this can be made larger than the other side. And then in that case, we have a supercritical branching process. So somehow we see that if you have many active individuals, then it's easier to have contact with them, and then you can have a big epidemic with positive probability. And the effect of dormancy is this factor of 1 minus Q. So somehow if you have dormancy with probability Q for unsuccessful virus attacks, then actually your active population size only counts 1 minus Q times. So you can actually, in theory, maintain a higher population size and you still don't get affected by a big epidemic. Of course, this is a bit tricky here because one can also think of dormancy having reproductive trade-offs, right? Which means that maybe it also decreases your active population size even further. But then at some point, there's also the question, okay, maybe this is nice against the epidemic, but if your active population size is too low, then maybe at some point some mutant comes without dormancy and this mutant can just fixate and wipe you out. So what one should definitely do, and I will also talk about that in the end at the open questions, it would be interesting to look at some version of this model where you have different host types, maybe one with dormancy, one without dormancy, and then see how these interact actually. Right, but now we see that this factor 1 minus Q really helps the active population. And then this constraint doesn't depend on kappa or sigma. So this means that there's, it doesn't matter whether all the dormant individuals die or all of them resuscitate because they are so few in the beginning of the epidemic that it doesn't matter what they do, basically. Okay, so that's the branching process. And then I also wrote here how to compute the extinction probability of the three-dimensional branching process. This is basically standard first step analysis. I wouldn't spend too much time on it, but it's these equations, which are actually of order m. So you don't always have an explicit solution if m is more than 4. But this way you can compute the extinction probability of the branching process. And then basically you start with one virus, then you have this S2. This is the extinction probability. And S1I is when you start with one infected guy, and S1D when you start with one dormant guy, and S1D is actually equal to 1. And basically, if the branching process is supercritical, so if lambda tilde, this largest eigenvalue is positive, then in that case, the probability of having a large epidemic should be basically 1 minus S2, because we just start with one virus in the beginning and no infected individual. And if lambda tilde is positive, then the exponential growth rate of the branching process, as Felix said yesterday, in a discrete time setting, is basically this lambda tilde is then the Lyapunov exponent when it's positive. So also when it's negative, but now I talk about the case when it's positive. And reaching a population size epsilon times k takes of order log k divided by lambda tilde time. So this should be the time until big epidemic. Okay, so this is what we can learn from the branching process. And then now we go to the dynamical system, because once we have this size epsilon times k, then we want to approximate our 4-dimensional rescale process with this dynamical system. So this is again this Lotka-Volterra type dynamical system. So basically what you have here in the first coordinate is similar to the case when there are no other types, right? So m1a dot of t is m1a of t times birth rate minus death rate minus this competition with all the other types 1a, 1d, and 1i. Then minus d n2 of t, this is the term loss of actives due to virus attacks. Then here's the resuscitation of the dormant individuals, recovery of the infected individuals. Then you get dormant individuals from the unsuccessful virus attacks and you lose them from the death and resuscitation. You get infected individuals from the successful virus attacks and you lose them due to recovery or death by lysis. And you get m new viruses from each death event by lysis. And then you lose viruses in the successful virus attacks, and you lose viruses also due to just natural death, degradation of viruses. And then I should talk a bit about related systems in previous literature. So Beretta and Kuang studied as a model for a marine bacteriophage infection in 1998. This system, but in the simpler case, when R is 0, so there's no recovery, every infected individual always dies, and there's no dormancy. So basically, three-dimensional version of this with R equals 0. And then Gulbudak and Weitz, which was one of our motivating papers for this project, they studied a four-dimensional system, but actually a simpler one. So they don't have virus reproduction there. They just look at the initial phase, first few hours of this virus epidemic. And yeah, this is the full system basically. And then the question is, what are the equilibria? So when does the right-hand side in each coordinate simultaneously become 0? And one of them is, of course, 0, 0, 0, 0. And everybody has died, every type has died out. But that's actually always an unstable saddle point if lambda 1 is greater than mu1. So we don't expect actually that the virus epidemic can kill the whole population, at least not in this deterministic setting. And M1A bar 0, 0, 0, so actives in equilibrium and no virus, no infected, and no dormant. This, then the question is, when is this stable? And related to this, when do we have a coexistence equilibrium? When do we have a coordinate-wise positive equilibrium, which we call M1A, M1B, M1I, N2? And if it exists, is it unique? And is it stable, right? That would be the ideal situation if we could answer all these questions, but unfortunately we are not yet able to answer all of them, but we can at least answer some of them. The first of them that we actually know is, when do we have a coexistence equilibrium? And what is nice that if you write down when do we have an equilibrium with 4 positive coordinates, you get precisely the same constraint here as for the branching process being supercritical. So somehow there's this correspondence between the stochastic system and deterministic system. If this is satisfied, then we have a coexistence equilibrium. And given that it exists, it's also unique. And it satisfies that the active coordinate of it, M1A, is obtained by dividing this right-hand side by this left-hand side. And this is always less than M1A bar. So this means that you see that type 1A actually suffers from this virus epidemic because you have a lower coordinate for the active population than without the viruses. And under this condition, when you have the existence of this equilibrium, then the equilibrium without viruses is unstable, M1A bar 0, 0, 0. When the strict reverse inequality of this holds, then actually M1A bar 0, 0, 0 is at least locally asymptotically stable. Okay, and then M1A, M12, M1I, N2, the coexistence equilibrium may or may not be stable. It depends on the choice of the parameters, and I will comment on that a bit later. But now, first, I want to say what we know independently of the choice of parameters. So what does always hold once we have this equilibrium? The first of, so we claim basically that if you start with some initial condition now where you already have a macroscopic amount of at least either infected individuals or viruses, it can be that, so we have all the coordinates in the initial condition are non-negative, we have a positive amount of actives, and positive amount of viruses or infected individuals. We don't have to have that both of them are positive because from the branching process, we get such an initial condition, but at least one of them is positive. Then we can have we can show 3 things. One of them is this persistence of the infection, or the coordinates of the dynamical system stay bounded away from 0. So for small enough beta, the linear of each of these coordinates is greater than or equal to beta. No extinction of viruses after this. Then also the active, dormant, and infected population size in total, this remains less than or equal to M1A bar minus beta for beta small enough. So even if you count dormant and infected individuals, you have less than without the viruses. And then there's this a priori bound MV, M1A bar divided by mu2 minus beta on the virus population. This is basically just saying that the virus population size is also bounded, and we can also somehow quantify how big it can be. You see that it's proportional to M. So if M is very large, then it can indeed get much larger, maybe a factor of M larger than the active population. And the proof for this is basically some generalization of the proofs of Beretta and Kuang for the case where there's no recovery and no dormancy. So R plus Q equals 0. and some small generalization is needed in order to treat the dormant coordinate. Maybe I should say that here, this thing that you can't converge to M1A bar 0, 0, 0, this is some kind of anti-Apunov function argument. So this Chetaev instability condition. And then we define this persistence set as beta for all the points that satisfy these three conditions. So all coordinates larger than or equal to beta and so on. This is a subset of 0 infinity to the 4. And then we want to somehow say that if we have a macroscopic epidemic, then we reach this set as beta also for our stochastic process divided by k. And now I can start talking about the main results, or putting together the things about the dynamical system and about the branching process. So, okay, so we had this epsilon parameter, right? And then we want to consider the limit k to infinity and then epsilon to 0. And basically, we want to show that the total infected plus virus population size reaches epsilon times k with probability tending to 1 minus this extinction probability S2, which may be 0 or may be positive, depending on whether the branching process is subcritical or supercritical. And if this happened, if you have a big, if you have macroscopic epidemic, so S2 is less than 1, that happens only in the supercritical case. Now we can approximate the rescaled stochastic process by the dynamical system. And then with high conditional probability, this rescaled stochastic process also reaches the set S beta for beta greater than 0 small enough. And then we define T as beta as the stopping time when you reach the set S beta. And we also define this T delta 2. This is the first time when the infected plus dormant population reaches delta K lower integer part. And in particular, T02 is the extinction time of types 1I plus 2. So basically, this is the time of the extinction of the epidemic. And then we want to show that for small epsilon at least, T epsilon 2 divided by log K, this behaves like 1 over lambda tilde. So lambda tilde was this Lyapunov exponent of the branching process. And T S beta divided by log K also behaves like 1 over lambda tilde, because the time in between is basically just some of finite order, because this is when the dynamical system approximation works. And then this happens with high probability on the event that you reach the set S beta before infected individuals and viruses die out. On the other hand, if they die out before one could reach the set S beta, then this should happen in a sub-logarithmic time. So this small O of log K time. And this should also hold when S2 is equal to 1. So in the subcritical phase, this should always be the case. Okay, so this is somehow the idea. And there's also this fantasy simulation here, which is of course not a simulation, but just drawing some curve. So what we should see that until time T epsilon 2 is the time when the dormant and, when the infected coordinate and the virus coordinate reach size epsilon times K. Until then, this active population should be very close to M1A bar times K, and the dormant population should be very close to 0. And when this happens, then suddenly, in a finite order of time, we go to this coexistence equilibrium. And if the coexistence equilibrium is stable, then we actually go very close to it and we stay around it. But it could also be that, for example, we have unstable coexistence and we have some periodic behavior, and then you should see here some macroscopic periods. But I will talk about the bifurcations a bit later. But the main point is that here, this is log K of order log K times, log K divided by lambda tilde, and this is here finite order of time. Okay, so now we can state the results. So assume that lambda 1 is greater than mu1, so type 1A is fit on its own, and lambda tilde is not equal to 0. So we don't look at the case when the approximating branching process is exactly critical. It should be either subcritical or supercritical. And then let's assume that at time 0, the active population size divided by K converges to this equilibrium M1A bar. And we just have 0 dormant individual, 0 infected individual, and 1 virus at time 0. Then for all sufficiently large, sufficiently small beta, the limit of the probability that you reach the set S beta, this coexistence persistence set, before types 1I and 2 would die out, this tends to 1 minus S2, where S2 was this extinction probability of the branching process. So S2 is equal to 1 for lambda tilde less than 0, when the branching process is subcritical, and it's less than 1 for lambda tilde greater than 0 when it's supercritical. Okay, so that's our first result. And then the second one says how long it takes to see that we are in this set S beta. So now we are in the case where lambda tilde is greater than 0. Then on the event that you reach S beta before infected virus would die out, this indeed Ts beta divided by log k tends to 1 over lambda tilde in probability, where lambda tilde was this Lyapunov exponent of the branching process. And then the last thing is, if we have an unsuccessful epidemic, so if it dies out early, then it dies out very early in the sense that the extinction time of infected individuals and viruses divided by log k tends to 0. And basically, the second one says that the active individuals and the dormant individuals don't really move away from their equilibrium. So the indicator that T02 is less than Ts beta multiplied by the norm of the difference between active population size and dormant population size divided by k, and the equilibrium M1A bar 0, this tends to 0 in probability, right? So in this case, the active individuals don't really fear that there has been an epidemic because it has died out so fast. Okay, and that's basically our result. And then, yes, so for the proofs, just a few more words. So the first phase until types 1i and 2 either die out or become macroscopic, this is the branching process approximation. And I have already mentioned the paper by Champagne, but actually we are using many concrete proof techniques by this paper that Jochen also mentioned yesterday. So Camille Coron, Manon Costa, Fabienne Laroche, Hélène Lehmann, and Charlene Smadi. This is about the emergence of homogamy in an individual-based stochastic model. And actually the biological context of their paper is not that important for us, but rather the proof techniques. And also we use this for our previous papers with Jochen, and we also adapt our adaptations from there. And for these techniques, it's actually crucial to work the branching process such that from any non-zero initial condition, it survives with some positive probability. So we can't have this three-dimensional branching process, but we have to actually use this two-dimensional one in this case. And then the second phase is once you are at size epsilon times k, then we use the dynamical system approximation, and reaching the set as beta is basically based on these persistence results on the dynamical system that I have told you before. So this is based on some arguments of Beretta and Kuang in the case when R is equal to Q equal to 0. Okay, and now comes the tedious question. Okay, we can prove this, but what do we actually know about the dynamical system? Maybe I should look at my watch for a second. So yes, so indeed, the coexistence equilibrium, when it exists, it's not always stable, but among certain conditions, it undergoes Hopf bifurcation, as you can see here. So basically, we have 3 critical burst sizes. So this M was the number of viruses produced in one lysis event. And the first one is M star. This is where the coexistence equilibrium appears. So if M is less than M star, then somehow the virus reproduction is so bad that the viruses just die out very quickly and the active population stays close to its original equilibrium. At M star, this is what we call the transcritical bifurcation point. Here, the coexistence equilibrium appears. And this is actually characterized by M1A bar being equal to M1A. So we have some equation for M1A, and that's what I showed you before. And that somehow coincides here with the active population size without viruses. And then afterwards, what happens first is that we have stability of this equilibrium, M1A, M12, M1I, M2, this is stable. And we have coordinate-wise eventually monotone convergence to this side. So now the viruses are actually persisting in the dynamical system, but we have this nice coordinate-wise monotone convergence to this equilibrium. And then M prime, this is a point where if you look at the Jacobi matrix of the dynamical system at this equilibrium, then we somehow switch from this coordinate-wise monotone behavior to this oscillatory convergence. So now we have 2 complex eigenvalues for the Jacobi matrix, but we still have stability. So in this oscillatory way, we converge to this coexistence equilibrium. You see that in the meanwhile, this is unfortunately quite small, but the red one is the virus component, and it's getting bigger and bigger because we have M larger and larger. So we produce more and more viruses. So this always gets larger. And then what can happen, but doesn't always happen, is that we have a Hopf bifurcation where these 2 complex eigenvalues cross the imaginary axis, which means that now they have a positive real part instead of negative. And at that point, instead of having a stable equilibrium, the equilibrium becomes unstable. And basically a periodic trajectory is the limiting, the omega limit set. So now we converge to this stable periodic trajectory. And yes, I will talk about this periodic behavior a bit more in a second. So we should start maybe the story from Beretta and Kuang. So what did they do? As I told you, R equals Q equals to 0. So no recovery, no dormancy. And then we have this nice three-dimensional dynamical system. And what they saw there, that indeed, in this case, this M double star is always finite. So if you look at M larger than M star sufficiently close to M star first, so just above the level where you have, where this coexistence equilibrium has emerged, then we have stability. But if you increase M further, at some point, at some M double star less than infinity, we have this Hopf bifurcation, and then afterwards we have this periodic behavior. And what is the problem with this periodic behavior from the point of view of active individuals is that if you have this high amplitude and low minima, right? So here you really have minima close to 0, for example. Then if you have a stochastic system approximating this dynamical system, then actually there you could have extinction of the whole population. So there's this danger of extinction. And this is very similar to what we know as paradox of enrichment in the predator-prey model. So what is the paradox of enrichment in a nutshell? So basically, there, instead of this M parameter, you have the carrying capacity of the prey. And if you have a low number of preys, then the predator can't establish, you just have the prey living at its carrying capacity. But if you increase the number of preys, then you have a coexistence between them, which is initially also stable. But if you put more and more preys to the system, then you will see this periodic behavior where first you have many preys, and the predator starts growing, but they overhunt the preys. So the preys start decaying, then the predator starts starving, they also decay, and then the preys have some chance to grow again. And then you have these big cycles. And that's the paradox of enrichment. And this is basically quite analogous to what we see in this virus model. Okay, so this happens for no recovery and no dormancy. And then now let's put recovery. So we still don't put dormancy, but we make R positive. And then actually looking at this Jacobi matrix at the coexistence equilibrium, which now has only 3 coordinates because we have no dormancy, then we see that if R is large enough, if we have a low enough mortality of this virus epidemic, then we can preserve the stability of the equilibrium. So at least for very large M, by the Hurwitz criterion, we can see that actually we have stability of this equilibrium. So recovery can help the host avoid this periodic behavior. And actually R greater than V is enough for this. So if the mortality is less than 50%, then for large enough M, we have, again, stability. I'm saying here large enough M because we haven't proven this for all M larger than M star, but actually we believe that for any M greater than M star, this should be true. So this means that there should be no Hopf bifurcation at all. But then if R and Q are both positive, then the analysis becomes more tedious because we have to look at the 4-dimensional dynamical system, and there also the Hurwitz criterion is much more complicated. And we only have some partial results and also some numerical things that I want to show you. So what is this? So here we have fixed parameters, positive R and positive Q. And this is M star. This depends linearly on, so okay, we fix Q and fix all the other parameters, and we only change R. So I play with the recovery rate, and I want to see where are my critical burst sizes. And M star, where the coexistence equilibrium appears, this is some linear function of R. And then also it seems, we don't know the equation, but it seems also that this other point where we have the emergence of complex eigenvalues, this also linearly depends on R. But the Hopf bifurcation point doesn't. So it starts growing, it grows more and more. And that in this case, R equals approximately 0.69, it explodes. So this means that if R is larger than this number, we never have a Hopf bifurcation, but we actually have stability of the coexistence equilibrium whenever it exists. And also, as I said, the same holds for Q equals 0. So for R larger than V, there's no Hopf bifurcation, and V is here 1.1 in this simulation. So that's one thing. And the other thing is now we fix we fix R and we play with Q. So Q is between 0 and 1. That was the probability of having an unsuccessful virus attack and dormancy. And then as Q tends to 1, actually everything should converge to infinity, right? So here diverge to infinity. So this is here M star, the transcritical bifurcation point where you see the emergence of the equilibrium. This tends to infinity as Q tends to 1. And the same holds for M prime. But for M double star, the Hopf bifurcation point, actually, the interesting thing is that here, already at some value a bit less than 1, approximately 0.93, this seems to explode, at least numerically. So this means that if Q is even larger than 0.93, if you have almost always non-successful virus attack and dormancy, then there will be no Hopf bifurcation. Then you can preserve the stability of the coexistence equilibrium. And this also holds for R equals 0. So if you have no recovery at all, just dormancy, then dormancy is still enough. If Q is very, very large, 0.97, then there's no Hopf bifurcation and no periodic behavior. So that's it basically for the simulations. And then in the last minutes, let's talk a bit about open questions, because of course that's why we are here. So one thing is that, yes, we haven't completed the bifurcation analysis. So we don't know for all choices of the parameters when we have Hopf bifurcation and when we don't have. And if we knew more about this, then we could also improve our results. So then we could also say about the stochastic system, not only that we reach this S beta, which is a quite large set, but we could also say that if we have stable coexistence, then we reach some small neighborhood of this equilibrium, this coexistence equilibrium, or if it's unstable, then we reach some neighborhood of this limiting periodic trajectory that we converge to. Maybe you have to shift this in time. Then, as I already started talking about this in the beginning, it would be interesting to look at different host species and some reproductive trade-offs. So maybe one of them with dormancy, one of them without dormancy, and maybe in chance with a higher reproduction rate. And this belongs somehow to the domain of attraction of adaptive dynamics in the case when we have a periodic initial condition, periodic initial behavior, and we plan some work in this direction with Charlene Smuddy. I mean, that's a more complicated thing because also these large deviation arguments in the beginning require some extension to this periodic behavior. Then other kinds of virus reproduction. So what happens if it's not lytic, but maybe chronic or lysogenic or anything else? And then other kinds of host dormancies are also interesting. So maybe you combine it with the competition-induced dormancy or anything else. And then dormancy of viruses instead of hosts. I think there's also evidence that that also happens in nature and in other situations, and that would also be interesting to study. And if I have 2 more minutes, then maybe 2 more pictures. One of them is that Jochen was very interested about in the beginning is Gulbudak and Weitz have this nice sentence. In the dormancy enhancement regime, nearly all of the target cell hosts enter dormancy even when there are far fewer viruses than hosts. So what is this? In fact, we can also observe this in our model, which is more complex than the one of Gulbudak and Weitz. But yes, so in the end, it's not that impressive because for that you have to make Q super close to 1. So this means that if Q is very large, like here, as Gulbudak and Weitz chose 50 divided by 51. So every 51 out of 51 virus attacks, only 1 is successful and 50 are unsuccessful. Then yes, the first wave of the epidemic here comes with this huge peak in the number of dormant individuals. And then you can also see that also the other waves of the epidemic, which is in this case periodic, you always have a big peak of this dormant coordinate. So that indeed happens, but it's maybe not that exciting in the end. And the other thing is large sigma. So what happens if sigma is large? This means that every dormant individual with high probability resuscitates very fast after becoming dormant. And this means basically that all these unsuccessful virus attacks are just as nothing would happen to these hosts. So the hosts are only affected by the successful virus attacks. And this means that we basically thin out these virus attacks. And we can, instead of looking at this 4-dimensional dynamical system with a dormant coordinate, it is very low anyway. So this is the dormant coordinate here at the bottom. We can just look at the case without dormancy, but with D, the frequency of virus attacks replaced by 1 minus Q times D. And then we really see no qualitative difference between the 2 dynamical systems, apart from the fact that there's no dormant coordinate here. Yeah, so this is, for example, here a case when we are here between M prime and M double prime, M prime and M double star, right? So this is not yet periodic behavior, but oscillatory convergence. And if you look at the previous one, this is clearly periodic. So this is larger than M double star. Okay, so that's what I wanted to say. Thank you very much for your attention.